Welcome back to our series on mathematical statistics. I'm Mark Ledbetter. This is video 33. We're in lecture 16, and this is the first part of that lecture for confidence intervals for the difference of means, and this is, of course, part 1. We're talking about a confidence interval for mu1 minus mu2. That's what we're looking for. Obviously, it's easy enough to either relabel mu1 as mu2 and mu2 as mu1, or so relabel population 1 or population 2, or you can just switch the order and find mu1 or mu2 minus mu1. Okay, and they'll be easy enough to do once we go through the derivations here. So let's suppose that we have two random samples that are taken independently from each of two populations, and this would imply, that the population 1 is independent of population 2. So we need some notation here to keep things straight. So we have the population parameters. So for population 1, the mean is mu1 and the variance is sigma 1 squared. And the same for, mu2 for population 2, the mean is mu2 and the variance is sigma 2 squared. For population 1, the sample size is n1. The sample mean is x bar 1, and the sample variance is s1 squared. And we have likewise, we can see the notation for population 2. Since the populations are independent, the samples are taken independently of each other. They're from two different populations, so that means that the populations are independent. Now you might say, well, when would they not be independent? If I have the population of height and the population of weight in the same, and we use the same individuals for both, they are not independent. My height is not independent of my weight, or actually I should say my weight is not independent of my height. Okay, so my height will help determine my weight or my propensity to be within a certain weight, right? So these things are dependent upon each other. They're correlated, so they're not independent. Okay? So if the populations are independent, then any statistic calculated from one population has to be independent of the statistic calculated from the second independent population. Okay, all the observations, if it's a random sample, then the observations from population 1 are all independent of each other and identically distributed in this case. And all the observations in population 2 are independent of each other and identically distributed. Well, if the populations are independent and all the observations within one population are independent, then it's very logical that the independent observations in the second population, all of those observations would be independent of any and all observations from population 1. So that means that these statistics calculated from a population of 1 that's independent of 2, that statistic, in this case x bar, is going to be independent of the same type of statistic calculated from that other population because the populations are independent. So these are independent random variables. All right. The cases we're going to cover in this section are only 3. So we are not going to cover the case where we know sigma 1 and sigma 2. So we don't know sigma 1 or sigma 2 in any of the cases we're going to cover. So we have larger sample sizes. So this means that both N1 and N2 have to be larger, at least 30. So equal to or greater than 30. For cases 2 and 3, either N1 or N2 or both are less than 30. So if just one of them is less than 30, you cannot use case 1. And in case 2, we're saying that we don't know sigma 1 and sigma 2, but we do know that they are equal, that it's common. Okay? And there are tests to do so, and we'll learn that in chapter 8. So we can simplify the notation. Since sigma 1 squared is equal to sigma 2 squared, we can just name that sigma squared. We don't have to worry about the subscript there. And then for the third case, not only are sigma 1 and sigma 2 unknown, but they're possibly different. And if they're possibly different, then we need to use this case. Okay? We want to find the standardized form of x bar 1 minus x bar 2. I want to remind you that this is going to be the statistic, so x bar 1 minus x bar 2 minus the expected value of that, or the mean, mu of x bar 1 minus x bar 2, divided by the square root of the variance of x bar 1 minus x bar 2. So that's the format. So for x, z of x is equal to x minus mu of x over sigma of x. Thus we need the expected value of x bar 1 minus x bar 2. Expectation is a linear operator, so we can think of distributing it across the summation. So we ended up with e of x bar 1 minus e of x bar 2, and that's simply mu 1 minus mu 2. Then we want the variance of x bar 1 minus x bar 2. I want to remind you that the variance of x is equal to the covariance of x with itself. So the variance of x bar 1 minus x bar 2 is equal to the covariance of x bar 1 minus x bar 2 with itself, x bar 1 minus x bar 2. And we have, so what we do here is we can use our property of covariances to figure out that we end up with the variance of x bar 1 minus 2 times the covariance of x bar 1 with x bar 2. Remember that the covariance of x bar 1, or x, let's just use x and y, is equal to the covariance of y and x. So the order doesn't matter. And that's what we end up with when we expand this expression for the covariance. So we end up with variance of x bar 1 minus 2 times the covariance of x bar 1 with x bar 2 plus the variance of x bar 2. This quantity is 0 because x bar 1 is independent of x bar 2. So that means that their covariance is going to be 0. And so we're left with, so the variance of x1 is equal to sigma 1 squared, and the variance of x2 is equal to sigma 2 squared. And so if we're taking the variance of a mean, remember it's sigma squared over n. So in this case, it's sigma 1 squared over n1. And for the second one, it's sigma 2 squared over n2. So this is the variance of x bar 1 minus x bar 2. You say, well, why is it a positive instead of a negative? Well, let's go back to our properties of, that's a good question, let's go back to our properties of covariance. So remember that the variance of x is equal to, let's just do negative x here. Let's say the variance of negative x is equal to the covariance of negative x, negative x. And we're going to say that A is negative 1 and B, so this is a covariance of A, X, oh, these are not X1s, they're just X. So we've got AX, AX. And if you remember, to calculate this, we take each of the constants. Let me make them different. Yeah, so they have to be the same because it's with itself. So -1 is a. So this means we bring out each of the constants and multiply them. So we take a times the covariance of x with x, which is equal to a squared variance of x. Well, in this case, this is a for that one is -1. So a squared is a +1, and that's why we end up with the positive. So the variance of everything always has to be positive, remember. We can't have a negative variance. It just doesn't exist. So this is our expression for the variance of x bar 1, x bar 2. Now we plug in. Here is x bar 1 minus x bar 2 minus its expected value, which is mu1 minus mu2. Notice the parentheses. These are important. Do not leave them out, or you will end up with the wrong number. And then over the square root of this whole quantity. Just remember that the square root of sigma 1 squared over n1 plus sigma 2 squared over n2 is not equal to the square root of sigma 1 squared over n1 plus sigma squared 2 over n2. Those are not equal. And you can plug in a few numbers, and show that that is certainly not true. Okay? So please don't do that. That is an awful thing to do. And we'll get you a few points deducted, quite a few. All right, since the population variances are usually not known, we cannot use this standardized form to construct a confidence interval. This would be the case that we're not doing. So for our case, we have n1 greater than 30, n2 greater than 30. We don't know sigma 1 and sigma 2, so we're going to replace sigma 1 squared and sigma 2 squared with s1 squared and s2 squared, respectively. And so this standardized version or form goes from at the top, the numerator stays the same. The denominator, instead of having the sigma 1 sigmas in there, we have s in there. And so since n1 and n2 are both greater than 30, then this is approximately distributed as a standard normal distribution. And what we want to do is we want to set, since it's approximately normally distributed, we can use z's. And so again, we're going to find, if this is z, mu is 0, we want to find a z naught such that the probability between negative z naught and positive z naught is 1 minus alpha. And then we solve for mu1 minus mu2 in order to get our confidence interval. And so, again, we'll want to multiply, because this is negative, okay, because these are negative, we want to multiply everything by -1, so we get probability of positive z naught, and we have to flip the signs. And we can use equal to here too, okay? It's greater than or equal to mu1 minus mu2 minus x bar 1 minus x bar 2. And then this is still over square root of s1 squared over n1 plus s2 squared over n2. Okay? Oops, wrong thing. Didn't mean to touch that. All right. I need to get rid of that parenthesis. It's wrong. Okay, so this would be divided by n2. Okay. So then we keep on working the algebra. We multiply, after we've multiplied by 1, or -1, then what we do is we do the same thing we did last time. We multiply both sides by this quantity here, or all three, I'm sorry, all three parts, or sides, if you will. So we multiply all three of these by the denominator here, which cancels it out in the middle. And then we take, let's see, remember we ended up with mu1 minus mu2 minus x bar 1 minus x bar 2. And this sign turned to greater than, that would be a positive, and over the square root. And then this would be greater than or equal to negative z naught. So we take this and multiply it here, and of course in the middle. And then we're left with just the numerator here. And so what we need to do is we need to add this negative, we need to add x bar 1 minus x bar 2 to all sides. So we end up with x bar 1 minus x bar 2 minus z naught times that square root. We have mu1 minus mu2 in the center, and then we have, got to clean this up so we can read it. Then we have, and the equal sign is just fine. Then we have x bar 1 minus x bar 2 plus z naught times this square root. And this probability is 1 minus alpha. So that means that our confidence interval is here. This is our confidence interval. And it can be written as, so the confidence interval for mu1 minus mu2 could be written as x bar 1 minus x bar 2 plus or minus z naught times the square root of s1 squared over n1 plus s2 squared over n2. Okay? So again, for calculation purposes, I like to write it this way because this quantity is the same quantity for both limits. So let's do an example. We have the systolic blood pressure measurements, and these are independent samples from two populations. In other words, and in this case, you'll see that they are independent populations, certainly. So what do we have? We have males and females. So they're definitely independent unless they're from the same family. We're going to assume that none of the males are related to the females and vice versa. So we have a sample size of 50 for each. Now remember, we don't have to have the same sample size. They can be different, but it does simplify the calculations when the sample sizes are equal. The mean for the females, the sample mean for the females was 117, which is lower than the mean for the males, which is 125. Likewise, this is a pattern you often see. The variance for the population with the smaller mean is usually smaller than the variance that goes with the larger mean. Okay? And so there it is. And we want to find the 95% confidence interval for mu1 minus mu2. Now, the first thing that we can do, these are very similar steps. So the first thing we need to do is find alpha. And remember that this quantity is C, which is in decimal form 0.95. And so we take 1 minus, so alpha equals 1 minus C. So 1 minus 0.95 is 0.05. Recall that, okay, so I didn't do it that way. Sorry. I have it correct. So I need to find, remember that we're looking at it this way, where we have 0.025, so because I divided by 2. So 0.025 over here in the lower tail and 0.025 in the upper tail. And here we'd have C equals 0.95 in this case. And all three of these has to add up to 1. All right? They have to add up to 1. And so I can look for z naught, which is z sub alpha over 2, which is z of 0.025 in this case. So we have 0.025 above z. That's the area above it, or probability above it. And so we go to our z table, and we look up inside, we look up 0.025. Now, our z-tables are different than z-tables in most of the introductory statistics courses, and it's good to be able to read these different tables. So table 1 is just like the tables you may have seen if you've taken an introductory statistics course. If you haven't, well, you did take, you were supposed to take, and I hope you did, and I know everyone this semester did, take probability theory, in which we learned how to use these tables. So table A, 5A, table 5A here, the areas inside the table are phi of z. This is the probability that, what do we call it here? Z naught is less than z is equal to phi of z, because phi goes with the standard normal. Okay, so probability that z is less than z naught, they called it z naught, so they should have used z naught here, or phi of z naught, and we call z naught and z naught and z naught. Okay, so we won't go through the integral, of course. So this is the cumulative distribution up to z naught. You'll notice they're all greater than, and these z's are positive, so it's all greater than 0.5, and we need less. So this table, here's z sub alpha, and so this is the probability that z is greater than z sub alpha. Okay? And that's exactly what it says here. And of course, in this case, it's going to equal alpha, and that's what they've put here. So in our diagram, we're looking for 0.025, and it's in the upper tail. That means we need to use table B. That's what this is. I went to the wrong one. So here we go. So this table is 5B. We need to use 5B, which is the upper tail. We need to find 0.0100 inside the table. I find 0.02, 0102, and 0099. This value is closer to 0.01 than this value. So we will not use it. We will use that. And we're looking for a z, so we have 2.33. Or 2.3 here, and then the second decimal place is a 3. So z naught is equal to 2.33. So that's our critical value that we're going to plug in to the equation. I'm sorry. We were looking for 0.025, not 0.01. So thinking of a different problem. So we need 0.025, I apologize. So inside the table, and please make sure you keep your decimal places clear. So I've got these three values. So I've got exactly 0.0250. I don't have to find the one that's closest. I just find it. So I need to find 1.9, and then the second decimal is 6. So z naught is equal to 1.96. I apologize for my mistake earlier. I had the wrong number in my head. All right. So 1.96 is our z naught. And so that is what we have put here. We found the critical value. Now we need to calculate using these values. So I'm going to write it over here. X bar 1 is 117. I'm trying to see my data. So 117 minus 125, that's going to be negative. I'm going to put a parentheses around this just to, you don't have to, but just to say that that goes together. And then plus or minus 1.96 times the square root of S1 squared, 41, over 50. So this is already squared, so I don't need to square it again. Be very careful with what they give you. They could give you S1 or S1 squared. And then plus 193.21 over 50. These have a common denominator. I can just add the numerator. And so what I end up with is actual values, negative 8 plus or minus 1.96 times the square root of 339.62 over 50. And this is equal to negative 8 plus or minus 1.96 times the square root of 6.7924, which is negative 8 plus or minus 5.108, and so forth. And so this is negative 8 plus or minus 5.1. And so, let's see. Yeah. So if I use one decimal place there, then, and I should, because blood pressures are whole numbers, so the averages should be one decimal place, right? So this is really 117 point, well, if I can get it to right, 0.0, and this is 125.0. Okay. Sorry, I should have used the same number of decimal places. Okay. So I want negative 8 minus 5.1 and negative 8 plus 5.1. And this gives me negative 13.1. And this gives me negative 2.9. And we are 95% confident, that's C, put C in there, that the interval negative 13.1 to negative 2.9 contains the population mean difference in blood pressures between males and females, and I put in parentheses females minus males. Using random samples of N1 equals 50 and N2 equals 50, you need to list both. Or you can say N equals N1 equals N2 equals 50. Okay? But you need to let the reader know exactly what you mean there. On the basis of the CI in Part A, is it reasonable to assume that mu1 is equal to mu2? Well, let's look at that. Mu1 equals mu2 implies that mu1 minus mu2 equals 0. So, can we assume that mu1 minus mu2 is equal to 0? And the answer is no, because the CI does not contain 0. The upper limit is negative and the lower limit is negative. So 0 is not in the confidence interval. If this were negative 13.1 to positive 2.9, then the answer would be yes. You say, well, what if it was negative 13.1 to positive 0.1? It would still be yes. 0 is inside the interval. It doesn't matter how close to the edge or it is. As long as it's in the interval, then in this case, 95%, at that confidence level C, we could say that they're equal. Okay? So let me erase the ones that aren't real here so that we make sure. Oh, I erased the wrong ones, didn't I? I want to erase this one. There we go. Okay, so as long as 0 is anywhere in the confidence interval, then we can say that mu1 is equal to mu2 at C, at the base, at C confidence level. So now, what if anything must be assumed about the two populations to justify using the confidence interval obtained in Part A? The book says nothing, but that is not quite right. Population 1 is independent of population 2, or you could say x bar 1 is independent of x bar 2. I prefer actually that you say this. Okay. This implies this. This does not imply that, actually. So most of the time it's true, but so what if I had blood pressure and BMI, but I did females and males? So I did female, or I did females only, and I said blood pressure, and I did, what did I just say? BMI. But so these are definitely dependent on each other if you're in the same person, but what if this group, what if these people were not the same as the ones used for BMI? Then, even though the populations are not independent, the averages are, because the way the samples were chosen, it's not the same female for both BP and BMI. Okay, so that's it for this first part of this section and this lecture. If you have questions, come to virtual office hours. If you need help before then, email me, but email me a picture of the problem so that I have it, because I may not have it available, and a picture of your work so far so I can see how you're approaching it, and this will help me help you both quicker and more thoroughly. Please stay safe, and because we hope to see you next time.